期中考试的成绩很好，almost everybody got between 70 and 100. The average is 86, so I'm pleased. But those who did not make 70, I think you better think carefully and perhaps talk to Professor Rang or Professor An about how you could do better later on this semester. It's clear that the average score of Tsinghua student is much better than my students at Stony Brook. So I'm pleased about that. 今天第一个 topic 是 gravity inside the Earth. 我们上回 talk about the shear theorem. 是说 if you consider the gravity due to this shear at a point inside the Earth, there's no force on it. Now for the next shear, there's also no force. So that means all the material in the Earth outside of this circle have together have no gravity on this point. The gravity on that point is due to all the material inside of that radius. So this gravity at O equal to gravity due to the material inside the sphere of radius r. Now, that material has a mass of is equal to 4 pi over 3 times r cubed. Well, we are assuming a uniform sphere. This is not true, but let us assume it's a uniform sphere. The volume of the sphere is 4 pi over 3 times r cubed. If rho is the density, then that material has a mass of this amount. By the shear theorem, on external points, the gravitational force at O is equal to all that mass being concentrated at the center. So it's equal to minus G times xiao m. Xiao m is the mass at this point times this density this mass divided by r cubed divided by R squared. This is G M, capital M, divided by R squared. And that is, of course, equal to something, something, something times R. A constant times R. So we now have the conclusion. Inside the Earth, the gravitational force is proportional to R. It's equal to 0 at the center, obviously, because at the center it's strictly symmetrical. There is no force in any direction. But as you go away from it, the attractive force becomes larger and larger, proportional to R, until you reach this point.关于这一点有没有问题？ Now we talk about section 10-6, gravitational potential energy, 引力的位能 ，potential energy 是位能。We want to prove that the potential energy is equal to minus G mm大 M 是小 m 是，比如说大 M 是 sun， 小 m 是 earth。我们先 take one dimension。假如 U 是这样子的话，我们从前说这个 force 是等于 minus du dr。我们 differentiate 这个呢，这个 minus just a second. This is equal to G M M R squared. Let's see, something is wrong. first there's a minus here, there's a minus sign here, and dd1 over r get the minus sign, so this is right. 所以假如你 u take 这样子的话，这个 force 是等于这个 correct， 所以 u 等于这是 correct。这是一个 one dimensional 的 problem。 How about the three dimensional? Three dimensional 的话要用所谓 partial differentiation。 Three dimension 的时候，这个 u 是等于 minus g m m r 现在是 x square 加 y square 加 z square， 现在是 three dimension 的了。那么对于 x y z 你要 differentiate 的时候叫做 partial differentiation。 That means when you differentiate relative to x, you consider y and z as fixed. When you differentiate with respect to y, you consider x and z as fixed. So 这个 notation 叫做 force， 是一个 vector， 是 du dx minus du dx minus du dy minus du dz。 这个 notation 是叫 partial differentiation。 这个有一个平常的这个那叫做 gradient。 三角形加一个箭头的意思就是三个 partial differentiation， partial x partial y partial z。 OK， 我们来试一下。假如我们 take 这个的话，那么 du dx 是等于 minus g m m 乘上 d u d 这个 square root， 然后 d 这个 square root dx。 这就是所谓 chain rule， 你在 differentiate 的时候，这是 minus g m m， 那 du d 这个东西呢，这 u 是 one over r。du d 1 over r 呢得 minus 1 over r squared， 所以这个是 minus 1 over d 这个 square root dx 呢是等于1/2的 square root。 1/2 1 over square root 乘上 d 这个 square root，d 这个 square root 的 inside 就是 x square 加 y square 加 z square dx。 因为这是中间的东西的1/2，所以 d square root of 一个 something 是等于1/2的 1 over square root of that thing 乘上 d 它里头的，所以就变成这个。 对不起，这还要乘上 dx square 加 y square 加 z square dx。这个你算了一阵以后，就得出来 g m m r squared 乘上 x over r。所以你这样算出来，这个 f 就等于 g m m over r square， 有个负号，因为这有个负号，乘上 x over r， 同样 y over r z over r， 它的三个 component。这个简写呢就可以写 minus g m m over r squared 乘上 r over r。这是什么意思呢？这个是这个 force。R over R 是 unit vector along the R direction， 所以比如说是这空间有一点，这个 unit vector 是 R over R， 因为 R over R 当然是在 R 的 direction， 它的 magnitude 是 1。所以这是 unit vector， 那所以这个 force 是对的 ，correct。In other words, we have proven that the U 是等于这个，在 3 dimension 的时候 U 也是对的。这个 formula 可以记得。是 force 是可以写成这样。Conservation of energy。我们现在有这个 formula F 是等于 minus gradient of U。gradient 的意思就是 ddx、ddy、ddz。可是我们知道这东西是等于 m 乘上 r double dot， 这是 Newton's law。所以我把它用 r dot 一下子 ，in other words， 我把它写成 minus r dot。这右边这是什么？右边这等于 ddt of 1/2m r dot r dot。你同意不同意 ？Because if I differentiate this, I can differentiate this one first, plus I differentiate this one. Both terms would give you r dot r double dot. So that two cancels this two. So this, and this is ddt of mv squared. That's our old friend, the kinetic energy. But what is the left side? The left side is minus d dr dt dot ddx plus 我把这 explicit 写出来，这等于 minus x dot times du dx minus y dot du dy minus z dot du dz。同意不同意 ？Because that's what's meant by the dot product. Dot product means 你把这三个 component 写下来 ，x dot y dot z dot， 这个 gradient 是 d dx d dy d dz。But once 你这样写是 du dx dx 是 dx dt du dy dy dt 这把这个就 means 是 minus du dt。So we have so putting these two together, we get d dt of u plus kinetic energy. So u plus 1/2 mv square is equal to a constant. And that's usually called E, total energy. This is, of course, something that we are familiar with. We have been familiar with already about the total conservation of energy. Now the only thing that's new is for the gravitational force. We know explicitly what the energy expression is. It's this U. Is minus gmm divided by r. Any questions? We may talk about the escape velocity, neglect air resistance.就是假如 on the Earth， 你从这个地方，你放一个 rocket with velocity v。Of course, the rocket has to overcome the resistance of air, but let us neglect that. Let us assume that the satellite or the rocket is already above the Earth's atmosphere. Let's say above 50 kilometers, there's essentially no more atmosphere. Does anybody know how the atmosphere goes down when you go farther and farther away? I'm sure you know that as you go farther and farther away from the Earth, there's the air pressure becomes less and less, and it's a complicated phenomenon because there's also temperature. There's a temperature variation, but roughly, when you go out, you know that the pressure decreases essentially exponentially. It's about every 5 kilometers, the pressure becomes half. So if you go very far, there's no more air pressure. So now let us start from that point. If I shoot a rocket at that point out, at what if If it's too slow, it will come down. It will be pulled down by Earth. The question is, at what velocity would it escape? Well, if it escapes, that means that because of the conservation of energy, that means that when it reaches infinity, it essentially has no more velocity. So, if it escapes, then E equal to minus G mm over R plus 1/2 mv squared must be greater than 0. Because 假如你的 R 非常大的时候，这项没有了，这个 has to be greater than 0. Because at R equal to infinity, E假如它能够 escape, that means that when 这没有一个 square， 它到 infinity 的时候 potential energy is 0, kinetic energy is positive, kinetic energy is always positive, so the total energy has to be positive. 等于0的时候是 just barely escape. That means 等于0 if E is equal to 0, that means it would go out, and by the time it reaches infinity, it has slowed down to V equal to 0. So that velocity is the escape velocity. So E equal to 0 gives escape velocity. And that, of course, is equal to 2m GMM. Yeah. In this case, m 等于 the mass of Earth.你要把它这个 number 放进去，是 2.38 kilometers per second for Earth. This number, if you estimate, is about 100 times the speed of a car, of an ordinary car. But of course, if you send a rocket from the Earth, you must first have enough thrust to make it escape from the atmosphere, and then you have to have this speed before it can go out of the Earth's attraction. There's an R here, sorry. one of the most important events in the history of mankind is the understanding of planetary orbits by Newton. In China, the ancient philosophers did not have, from today's viewpoint, the correct view about the structure of the universe. The Greeks also had an incorrect view, but their way of thinking about it eventually led to Newton's discovery. First, in the Greek times, the most important person was Ptolemy.他是公元90年到168年在希腊的。那么 the way that he was thinking, and in fact the way all the Greeks were thinking, was that the earth is at the center of the universe. 所以叫做地心说，地心学说。And furthermore, they had the following feeling. They wanted to construct a universe which is most beautiful. Because they believed God must create a most perfect, most beautiful structure. And what is most beautiful? The circle is most beautiful. 所以他们叫做 harmony of circles. They thought that the earth is at the center of the universe, and the stars, the planets, would all go around in circles. But that's not correct. By observation, they knew that, for example, the motion of Mars is very complicated. So they thought it's not a circle. The next complicated but beautiful thing is a circle on a circle. 什么叫 circle on a circle 呢？假如你这上头有一个球，有个圆圈 while the center is moving in the big circle, there's a particle which goes around this, so you would get something like this. That's called circle on circle. And they tried to adjust the sizes of these two circles to make it match the motion of the planets. It didn't work. So they make it a circle on a circle on a circle. And since there are many planets, so there are many circles. And at one point, somebody had the complete structure of the planet's motion. There were 80-some circles. And that was the general way of thinking about the planetary motion. Now, why are planetary motion so very important? Because there's agriculture. When you develop agriculture, you know that agriculture depends on the understanding of the seasons, and understanding of the seasons depend on understanding of the motion of the stars around the earth. as you see them. So this is that astronomy is an important subject in every civilization. It's an obvious thing, because if you develop agriculture, then astronomy becomes important. But there are regularities of the motion of the stars, of the planets, but there are also strange motions. So people began to try to puzzle out these strange motions, and therefore the circle on circle on circle kind of idea that held back Western astronomy for more than 2,000 years until Copernicus. He advocated heliocentric theory. 日心，太阳是在心里头。You all know that Galileo subscribed to this theory. Galileo believed in this theory and was persecuted by the Catholic Church. Nevertheless, many astronomers began to think about the heliocentric theory, 日心的学说. The next important development was Tycho Brahe. "他们都是中国的明朝时候的人。Tycho Brahe was an observer. He made accurate measurements of the position of various planets year after year. And after he died, his data was analyzed by Kepler. So Brahe was an experimental astronomer. Kepler was a theoretical astronomer. It was very interesting how Kepler made his great discoveries. He concentrated on the motion of Mars. And the motion of Mars, according to the Copernicus idea, was mostly a circle. In fact, the orbit of Mars, as we know it today, is almost a circle. But because Brahe's data was very accurate, so Kepler was able to accurately map the position of Mars and found that it's not a circle. It doesn't fit a circle. It almost fits a circle, but not quite. And then one day, he suddenly realized it's not a circle at all. It's an ellipse. This is one of the most important events in the history of mankind. The reason that he could land on the idea of an ellipse is also because the Greeks had studied ellipses in detail. We all know, and I'm sure you have learned plane geometry, Euclid's geometry, in high schools. But the Greeks developed geometry much more than Euclid. After Euclid, they studied what is called conic section. A conic section is you take a cone, take a circular cone, and you can cut it. If you cut it this way, obviously it's a circle. If you cut it this way, it's an ellipse. So this way you get a circle. This way you get an ellipse. If you cut it this way, then it has two branches, one cut in the top, one cut in the bottom. You get a hyperbola. Circle 是圆 ，ellipse 是椭圆 ，hyperbola 叫做抛物线。All of these curves, their relationship to each other and their relationship to the cone were studied in great detail, beautiful work in Greek times after Euclid. And Kepler, being a theorist, knew these conic section results very well. That is perhaps the reason why it dawned on him one day that the reason that one cannot fit a circular orbit to the trajectory of Mars was because it's not a circle, it is an ellipse. And once that's done, he formulated the three laws. These laws, in today's language, are called empirical laws. Empirical 就是经验的，是经验的或者是实验的。它的第一个 law 是说 planetary orbits are ellipses. With the sun at one focus. 一个 ellipse 永远有两个 focus。一个 ellipse 它有个东西叫做 ellipse， 叫做 eccentricity。eccentricity 我想叫做椭圆律，是不是？椭律。这个 eccentricity 等于0的时候，它是个 circle， 等于1的时候，它就变成是等于1的时候，它是抛物线；大于1的时候是 hyperbola。We'll come to this later. So the first law says that all planetary orbits are ellipses, and that was very accurately correct for a long time. Then, of course, when people had more accurate measurements, they found slight corrections to this, and that correction needed additional considerations. That's outside of our discussion this semester. The second law says that a planet sweeps the same amount of area each unit time。这句话的意思是这样，就是这个 satellite 这个 planet 在走的时候，比如说在一个单位时间，它这一个小三角形在另外一个单位的时间，这些三角形是同一个面积 as it goes around。A planet sweeps the same amount of area each unit time. The way that he formulated this law shows that he was a very geometrical person. He used he evidently plotted the curves and observed that when the planet moves slower, that when the planet is farther from the sun, it moves slower, but this distance is longer, and this area becomes the same. So when it comes to here, it moves very fast, but in the unit time, it still sweeps the same area. The third law says the period cubed divided by T is the period around the sun. A is the semi-major axis. 从这一点到这一点 that distance is called 2a. 不同的 satellite all around the same sun share the same value of t cubed divided by t squared divided by a cubed. Sorry, t squared. Kepler died in the year 1630. A few years later, Newton was born. Newton explained. Newton was both an experimentalist and a theorist. He was a great experimentalist as well as a theorist, but perhaps his greatest contribution to mankind was his discovery of calculus, of the planetary, of the origin of the planetary motion, or the origin of Kepler's laws. The most important contribution of Newton was he explained the three laws, Kepler's three laws, through the theory of gravitation. These three laws are explained in the book but it was too simple because it did not succeed in proving the three laws. We are now going to go through the proofs of all three laws. So first, proof of second law. The second law is the easiest to prove. We had the following theorem. Several weeks ago, we had proven this theorem by straightforward differentiation. If this is the sun, and this is the earth, and this angle is theta, this distance is r. That's called polar coordinates. Using polar coordinates, we found the acceleration has two components. One is along the direction of r, the other is along the direction of theta. This is the direction of r, and the direction of theta is perpendicular to it. And so, let us apply Newton's law. Newton's law says that the force is equal to ma. You multiply this by m should be equal to force. But the force is only in the r direction. So therefore, the theta direction has to be equal to 0. You know, the Newton's law says 2 r dot theta dot plus r theta double dot is equal to 0. There's another. We also know that this acceleration, m times that, m times r double dot minus r theta dot squared, has to be equal to minus g m m over r squared. That's the meaning of F equal to ma. Okay, let's take the first one. That one means d dt of r squared theta dot. That's equal to 2r r dot theta dot plus r squared theta double dot, just by straight computation. And that has to be equal to 0, because let's call this 1, this 2. Therefore, r squared theta dot is equal to a constant. R squared theta dot is equal to r times r theta dot is equal to a constant. Now, this is r.这个角是 r theta dot， r theta dot dt 是这个角度。Therefore, 1/2 but 1/2 of r 乘上 r theta dot dt 是等于 area swept in dt， 这等于 1/2 of r square theta dot dt 等于 1/2 c dt。 In other words, area swept in dt 是一个 constant 乘上 dt, and that's second law, i.e. 就是这个 area swept 是 proportional to dt， 是个 constant 乘上 dt。 But r 乘上 r theta dot is also the angular momentum explanation. r 乘上 r theta dot 等于 constant is equivalent to conservation of angular momentum. In other words, the second law of Kepler is nothing but the conservation of angular momentum. As long as the force is always along the direction of r, there is conservation of angular momentum, and then there is Kepler's second law. In other words, suppose the force is not 1 over r squared, it's 1 over r cubed, or 1 over or anything which depends only on r, but with no theta component, then second law always is correct. I.e., second law follows from angular momentum conservation plus central force. Central force 的意思就是 the force is always directed to the center. In other words, no theta component. Next, we are going to prove the first law. But before we do that, let me box this equation. R squared theta dot is equal to constant. Now we go to the equation 2. Equation 2 becomes r double dot minus r theta dot squared is equal to minus gm over r squared. In fact, let's put the m back in. 我两面都乘上 r， 然后integrate， 我就得出来 m 2/2 m r dot squared 加上 r squared theta dot squared 要等于 minus g m m r。假如我 differentiate 这一项就变成了这个乘上 r dot， 这一项就变成这样好 let's forget about this. It's simpler that we directly use the energy law. We know the energy. We have proven 20 minutes ago that the total energy is kinetic energy 1/2 mv squared plus u, which is mmg over r. That is equal to a constant. This actually follows from this. Only you integrate this, you multiply this by r dot and integrate, you get this expression. But since we have already the general statement, so we might as well start from here. This is the kinetic energy, this is the potential energy, and that the result is equal to constant. We call it E. And again, we divide the case into E equal to 0, E greater than 0, or E less than 0. For a particle which can go to infinity, which can barely go to infinity, E is equal to 0. If E is greater than 0, that means that when R is infinity, this part is positive, so it can go to infinity with a finite velocity. If it is negative, this part cannot become 0, because if this part is 0, this is positive. If E is negative, that never obtains. In other words, case 1, E less than 0, cannot escape. This is the case that we'll deal with first. Later on, we'll deal with E equal to 0 and E greater than 0. So let us write E is equal to 1/2 of m. V squared is r dot squared plus r squared theta dot squared minus m g over r. R dot is equal to dr d theta d theta dt, so I can write it this way, and therefore this is equal to 1/2 of m dr d theta squared plus r squared times theta dot squared. But theta dot but we have r squared theta dot equal to a constant. We had that formula before, according to the second law. So I can use that to eliminate theta dot. So this becomes it's c squared over r4. Let us now multiply this whole by r4. So we get E r4 is equal to m over 2 我把它规避的 formula 我都是这个 E 是 negative， 所以我 write minus a squared to be equal to 2e over mc squared。 我把这个一乘了以后，那个 e 的那一部分就变成这个。注意 e 是 negative， 所以我写成 minus a squared。 b 呢是等于 2mg over c squared。 这个方程式很多年以前 of course 我看见了，所以昨天我就试来解这方程式，越解越复杂，后来讲了半天以后，我记得一个 trick， 这个 trick 是这样，得要换一个 variable， 你要用这个 r 的话，这个你可以把这个 r 拿到这边去，然后开一个方针，开一个平方。Then you get dr d theta, and then you divide after you get theta. It's an integral over dr of a complicated expression. You can do it that way too, but that's not the easy way. Then I remembered there was a trick. I don't know who first found the trick. Newton must have found the equivalent trick, but he did not write it in his book. The trick is to invert r. Put r equal to 1 over rho. Then dr d rho, dr d theta becomes dr d rho, d rho d theta. But dr d rho is equal to 1 over rho squared. So we put that in there, you get 1 over rho fourth, d rho d theta squared, plus 1 over rho squared is equal to minus a squared over rho fourth, plus b over rho cube. You multiply by rho fourth, you get d rho d theta squared is equal to minus a squared plus b rho minus rho squared. The advantage of this compared with this, it's very similar. But here dr d theta has r square term, r cube term, r fourth term. In rho, it has become constant rho and rho squared. So this is simpler than this, and that's the trick. When you have something like this, the natural thing is to perfect the square. So this is a minus rho minus b over 2 squared plus b squared over 4. That takes care of these two terms, minus a squared. So let's call this sigma squared. So we put sigma equal to rho minus b over 2. R 等于 1 over rho. Then this becomes d sigma d theta squared is equal to minus sigma squared plus k squared, where we define k squared to be b squared over 4 minus a squared. How do I know it's a positive number, not a negative number? It can't be negative because the left side is positive. So unless this is positive, the equation doesn't make sense. When you have an equation like this, by inspection you know what to do. You should write sigma as k sine theta, sine phi. Put. When you do that, d sigma d theta becomes k cosine phi d phi d theta squared is equal to k squared minus k squared sine squared theta sine squared phi, which is equal to k squared cosine squared phi. The reason that we do this is because the k squared cosine squared phi cancel. So we get d phi d theta equal to 1. So d phi d theta is equal to plus minus 1. We need only consider d phi d theta equal to 1. So therefore phi, we can write phi is equal to theta plus a constant. So we put that back in. We get rho is equal to 1 over r is equal to b over 2 plus k sine of phi theta plus constant. The constant doesn't matter. All it means is you change you rotate. You change the origin of theta. So I can make that constant equal to 0. So I would get 1 over r is equal to b over 2 plus k sine theta. I can write this as b over 2 times 1 plus e where E is equal to K, 2K over B. It's 2 over B times K. K is square root of B squared over 4 minus A squared. So therefore it's equal to square root of 1 minus 4A squared over B squared. And that is equal to square root of 1 minus 2C squared over M squared G squared times minus E over M. This is a very important quantity. It's called the eccentricity. It tells you how ellipse, how much it deviates from a circle. Let's look at the expression. It's a square root of 1 minus c. C is related to the angular momentum, how much it sweeps per unit time. M squared, G squared are related to the mass of the sun and the gravitational constant. Minus E over M. E is the energy of the planet. That E is clearly proportional to M. In other words, if the Earth were twice as massive, you can think of it as two Earths stuck together, and each of them would still follow the same orbit. So therefore E is always proportional to M. So E over M is the per unit mass energy for the planet. And we get this, and this is we shall now show that it is an ellipse. It is an ellipse because this is another trick. When you have an equation which has R in it, you always follow what we are going to demonstrate as a trick. I take this formula and multiply it both by R, so I get 1 is equal to B over 2 times R plus E times R sine theta. R sine theta is Y. You have an equation which both has x, y, z in it and has R in it. The way to do it is to move everything to one side which does not contain R and then square it. In other words, you get 1 over B over 2 EY is equal to B over 2R. Now I square both sides. So I get 1 minus B E Y plus B squared E squared Y squared over 4 is equal to B squared 4 R squared, which is X squared Y squared. This way we get rid of the R. R has a square root and it's not convenient. Now if you look at this, it is an ellipse. this is E is less than 1. How do I know it's an ellipse? Because you know, when you have a quadratic equation in x and y, we'll show that it's an ellipse in a minute. Let us multiply this by 4 over b squared. Multiply it by 4 over b squared. I get 4 over b squared minus 4ey over b plus e squared y squared is equal to x squared plus y squared. So I get 4 over b squared minus 4ey over b is equal to x squared plus 1 minus e squared y squared. I shall define this I get 4 b squared is equal to x squared plus 1 minus e squared times y squared plus 4e divide 1 minus e squared, 2e. 1 minus e squared y squared plus this is 2ey. This is 2ey over b minus 4e squared over b squared 1 minus e squared. What I'm doing here 就是配成平方，我把这个搬到这边去，把它配成平方。我现在 define 一个 alpha， 我看我这做的对还是不对啊？我现在 define 一个 alpha square 等于4 over b squared。那么你去把这个方程式化简了一下，你就得出这个 x square 加上1 minus e square 乘上 y prime squared is equal to alpha squared plus e squared alpha squared 1 minus alpha 1 minus e squared， 这个东西就等于 alpha squared over 1 minus e squared，where y prime 是等于 y 加上 2e所以你看这个方程是一个 x square， 这是 1 minus e square 是 positive， 所以这是一个 typical 的 ellipse 的样子。你要把它写成 standard 的样子呢，你得写成这样，把整个这个倍值除一除。这个现在变成了一个 standard 的 ellipse 的样子，这个我想你们都有 recognize it。这个的数目比这个数目大，因为这又被一个 1 minus e square 除，所以它的 major axis 叫做 A semi major axis， 就是它是个 ellipse 是这样的。我看对不对？对。它的 semi major axis 就是这个 A。是等于 square root of 这个东西，是等于 alpha over 1 minus e squared。这叫 A。minor axis 叫做 B， 是这个距离。这个等于什么呢？等于 square root of 这个，等于 alpha。QED 了，我们现在证明了，说是这个的 orbit 是一个 ellipse， 说是这个 ellipse 的这个原来 shift 过以前 y prime 等于 y， 这 shift 以前这是一个center， 这是一个 focus。这个我们不去证明了，这不你可以去你试一下，就是它有 standard formula， 你知道 major axis、minor axis， 你就知道它的 focus 在什么地方，你就发现那个 focus 在的地方真正是刚才 y 到 y prime 那个 shift。OK， 现在还有第三个 proof of third law。The third law 是告诉你它的 period 跟它的 major semi-major axis 是有一个关系。这个我们利用它的这个area of ellipse。大家晓得 area of 一个 circle 是 pi r squared。假如变成一个 ellipse， 有个 major axis 有个 minor axis a 跟 b， 那它的这个 area 是 pi a b。假如 a 等于 b 的话，就变成 pi a squared。所以我们可以知道，因为刚才我们又有 major axis 又有 minor axis， 所以就得出来 alpha squared over square root of 1 minus e squared the cube。Now, 1/2 of r squared theta dot， 这个是等于 d dt of area swept。这个方面呢，我们从前有，因为就是。This is r, this is r theta dot dt. So 1/2 of that is equal to area swept. 1/2 of that is area swept per unit time. 那所以假如而这东西是等于 2c， 这等于 c over 2， 因为 r square theta dot 是等于c， 所以整个的 area， 所以 total area of ellipse divided by the period， 这就等于这个。因为这个东西既然是 per unit area， 那这个 total area divided by t 当然就是这个。所以我们就知道这 area， 所以 area total area 等于 tc over 2， 可是这等于 alpha squared over square root of 1 minus e squared cube， 所以我们就得出一个 formula， 这个我们算出来这个 period 是等于 2 over c total area 等于这个派 alpha squared over square root of 1 minus e squared cube。 然后我们又知道 a 是等于 alpha over 1 minus e squared， 这是我们刚才有的 formula。所以呢，我们就可以算 t squared over a cubed。这个 algebra 你算了半天以后，就证明这是等于 4 pi squared over mg。这个在书上有。不过书上没有证明，书上因为书上根本没有讲这 ellipse， 它顶多有时候 talk about 这个 circle 的 case。现在我们这是证明是 general 的，而这个当然就是 Kepler's third law， 说是 t squared over a cube 是一个 constant， 只 depend on the sun's mass， 不同的 planet 有同一个这个 constant。So we have proven all three all three Kepler's laws. Next time, we are going to discuss the other two cases, namely E is equal to 0 and E is greater than 0. I'll be in my class, in my office this afternoon between 4 and 5.